So the Weierstrass substitution looks like this. We're going to let u equal tangent of x over 2. So we put u over 1 and fill in the right triangle. And so first, I'd like to get my hands on sine of x. And in order to do that, I'm going to use that double angle formula I just mentioned for sine. So sine of x is equal to 2 times the cosine of half of x times the sine of half of x. And that's nice because we can use our right triangle, figure those out. Let's go ahead and do that. So cosine here adjacent over hypotenuse, that's going to give me 1 over the square root of 1 plus u squared. And then we go ahead and take the sine, so opposite over hypotenuse gives me the following. And of course we can just tidy that right up. So it looks like we've got 2 times u over 1 plus u squared. Okay, so let's go ahead and find the cosine of x. So cosine of x by the double angle formula, that's cosine squared of half of x minus the sine squared of half of x. Again, that seems nice. We can use our triangle. Let's see what we get here. Okay, so we're going to take the cosine adjacent over hypotenuse and then square it, minus the sine, which is opposite over hypotenuse, squared, and we get the following. So this looks like 1 minus u squared over that nice common denominator of 1 plus u squared. So this is kind of nice for both cosine and sine because it follows that previous video we talked about, the unit circle. We did a rational parameterization of the unit circle, and we got exactly these quantities for cosine and sine. So check that video out. It's pretty nice, and see if you can find nice little connections between what we did in that video and this. Okay, so with that said, let's go ahead and find the tangent of x. So we can find the tangent just by stacking sine and cosine. Okay, so tangent of x, that's equal to sine of x over cosine of x. But we just said that sine was 2u over 1 plus u squared. And cosine, well, that's 1 minus u squared over 1 plus u squared. Those will cancel. And for tangent of x, we get 2u over 1 minus u squared. Okay, so let's take what we know about sine, cosine, tangent, and define maybe all 6 of the classic trig functions. Okay, so quickly from before, we know that sine is equal to 2u over 1 plus u squared. We know that cosine of x is equal to 1 minus u squared over 1 plus u squared. And we just saw that tangent was equal to, looks like 2u over 1 minus u squared. And just by taking reciprocals, we get cosecant. So that's 1 plus u squared over 2u just by flipping sign. Secant, just by taking the reciprocal of cosine, gives us the following. So that's 1 plus u squared over 1 minus u squared. And then cotangent. So cotangent of x must be 1 minus u squared over 2u. Okay, so maybe I want to make some more observations here. So that seems nice. And yeah, let's note something. So I'm going to say since u is equal to tangent of x over 2, we have the following. So we could write this in terms of its inverse function, arctan. Let's do that. So arctan of u should be x over 2. And then we could just solve for x, right? We could say that, well, x is equal to 2 arctan of u. That proves to be nice in the realm of integration because we can use this to find dx. And so dx is equal to 2 over 1 plus u squared du. Okay, so what we want to do now is apply this in the realm of integration. Okay, so for example, let's say we want to compute the integral of 1 over 1 plus secant of x dx. So recall from our substitution that secant of x was exactly 1 plus u squared over 1 minus u squared. And then also, we said that dx was equal to 2 over 1 plus u squared du. So that'll be pretty handy. So let's substitute those in, be ready for some algebra. Okay, so let's see here. dx, so I've got 2. So using this, it looks like 1 over, or du over 1 plus u squared. Let me say du, that's fine as well. Okay, so that's fine. Next, the secant. So I've got 1 plus, looks like 1 plus u squared over 1 minus u squared. Okay, so there's the secant of x. Okay, so maybe I'll hold off on distributing this. I'm not a huge fan of these complex fractions that are going on here, so I'd like to get rid of that. So let's go ahead and multiply the top and the bottom by this quantity, again with the hopes of getting rid of the complex fractions. And so I'm going to multiply the top by this 1 minus u squared. And if I multiply the bottom by 1 minus u squared, that's going to distribute here and then cancel with this. So I've got this 1 minus u squared plus this 1 plus u squared, and then sort of waiting on the outside is this 1 plus u squared. Okay, so that seems pretty nice. Maybe we can tidy this up. And of course, don't forget your du. And so let's see what we have here. So here the looks like the u squares are going to cancel. I've got 1 plus 1, which is 2. That seems nice. And so I've got this 1 plus u squared business downstairs. So the 2's are going to cancel. And it looks like I have a rational function that I'm trying to integrate where both the top and the bottom have the same degree. So that seems pretty good. We can go ahead and do long division. So I've got 1 minus u squared here. I've got 1 plus u squared here. And again, since the degree of the numerator matches the degree of the denominator, we'll proceed by long division. So I'm going to write the numerator like this. Negative u squared plus 0u plus 1. And that's being divided by the denominator. Okay, so I'm going to write u squared plus 0u plus 1. Okay, so let's see here. So u squared goes into minus u squared minus 1 times. So I'm going to multiply, so distribute, and then subtract. So this is negative u squared. This will be 0u still. This will be minus 1, but of course we have to subtract that. So that gives me a remainder of 2. So that's 2 over 1 plus u squared, right? That's really 1 plus u squared. So that seems pretty nice. So that's going to give us the following. So we've got minus 1 plus 2 over 1 plus u squared. And so the antiderivative of minus 1 in respect to u, of course, is minus u. We recognize this as an arctan form. So that's 2 times the arctangent of u. plus c. And we just want to recall a couple things. So let's recall from our substitutions. So from Weierstrass, we know that u is equal to tangent of x over 2. And we know that, well, just by rearranging, right, that arctan of x, or I'm sorry, arctan of u rather, is equal to x over 2. So that seems pretty nice. And so let's go ahead and substitute back in. So this looks like negative tangent of x over 2, because again, u is tangent of x over 2. And then we've got 2 times the arctan of u, but the arctan of u is x over 2. The 2's will cancel, and so I'll write this with the minus in the middle. So I've got x minus the tangent of x over 2 plus c. So pretty neat use of our substitution. Okay, so yeah, let's go ahead and try another one. So let's try, for example, let's try to integrate 1 over 1 plus cosecant of x dx. And so remember that, not cosine, cosecant. Cosecant. So this was the flip of sine, right? So this was 1 plus u squared over 2u. So that seems pretty nice. Be nice to also replace this dx. And so dx is equal to 2 over 1 plus u squared du. Okay, so let's see what we can do here. Okay, so inside my integral, I've got 1 over 1 plus. So I've got my cosecant here. So my cosecant is 1 plus u squared over 2u. And then replacing dx gives me the following. So I've got this 2 over 1 plus u squared du. And just like before, I'm not so thrilled about the complex fractions. So let's multiply the top and the bottom by 2u to get rid of this, and then we'll deal with that a little bit later. So yeah, multiplying both the top and the bottom by 2u gives me the following. So I'm going to have 2u times 2, so that'll be 4u. And then I'll have 2u here. And again, this 2u will cancel out. I've got 1 plus u squared. And then I've got this 1 plus u squared business here. Okay, so that seems pretty good. I can rewrite this. So I've got 4u. I'm going to write this first. That's 1 plus u squared, or u squared plus 1, doesn't really matter. And then here I could factor this, right? Because that's u plus 1 quantity squared. And so this looks like a classic partial fraction decomposition problem from calculus. And so that's how we're going to proceed. Let's go ahead and do partial fraction decomposition on this thing. Let's see what happens. Okay, so putting the calculus to the side, let's deal with the algebra. I want to break this down. So let's see what we have here. So 4u. So I noticed this quadratic unique factor. So we know how to decomp that from calculus. And then I see this linear repeating factor, or factors. And we know how to deal with that as well. So we know this, we're going to deal with this as au plus b over u squared plus 1. And then since this is linear repeating, I'm going to need c over a copy of that to the first plus d over that quantity squared. Okay, so that seems pretty good. We're going to multiply through by the LCM of the denominators. Kind of get rid of this fraction here. So that's going to be, it looks like u squared plus 1 times u plus 1 quantity squared. Okay, so let's distribute through and cancel, clear out all those denominators. That's going to give us the following. So I've got 4u equals, looks like au plus b. And then this will cancel with this, leaving this. So that's u plus 1 quantity squared. One factor of u plus 1 will cancel out here. So we've got c times u squared plus 1 times 1 copy of u plus 1. And then here, both factors of u plus 1 will cancel, leaving me with d times u squared plus 1. Okay, let's see if we can find a, b, c, or d right off the bat. And so, yeah, let's notice this. So if u is equal to minus 1, that'll make this drop out, we can find d. So yeah, let's observe the following. So if u is equal to minus 1, then we get minus 4 equals 2d. And so that forces d to be minus 2. So we've got 1 right off the bat. Okay, well, I don't want to deal with imaginary complex numbers right now. I'm going to keep it real. So I'm going to expand this out instead of plugging more things in. But if you wanted to play around with imaginary numbers, you could do that as well. So instead, let's go ahead and expand this out and work towards equating coefficients. Okay, so let's expand that out first. So I've got au plus b. This is u squared plus 2u plus 1. So that seems fine. Let's go ahead and multiply those out. So it's going to be, it looks like u cubed plus u squared plus u plus 1. That's not bad. And then I'll just wait for this. And then I'll go ahead and expand further. So this seems okay. So here we want to be very, very careful here. So I'm just distributing. So this will be, it looks like a u cubed plus 2au squared plus au. I'm going to double check that. That seems good. That seems good. Yeah, so I think we're okay so far. So distributing the b gives us the following. So we've got b times u squared plus 2bu plus b. Again, I'm going to double check. Good, good, good. Okay. It's always a good idea to double check. It really is. So that seems good. And then lastly, distribute the d. So du squared plus d. And so I just want to organize by types. So cubes, I'll denote cubes like this. Squares, I'll denote the squares with a square, pretend that's a square. Okay. The linear terms, I'll denote with a little line segment, I guess. And then my constants, let's denote with stars. That just keeps me organized. Okay, and then let's group like objects together. So cubes, looks like we have 2 cubes, so a plus c times u cubed. That takes care of all of our cube terms. Next are squares. We have 2a plus b plus c plus d. And then our linear terms. So for linear terms, I've got a, 2b, and then c. And then our constants. So for constants, looks like b, c, and d. Okay, so now we can go ahead and equate coefficients. So the coefficient of u cubed on the right must equal the coefficient of u cubed on the left. And that coefficient must be 0 on the left because nothing else would have made that disappear. So the coefficient of u squared must equal the coefficient of u squared on the left, but again, on the left, that coefficient of u squared must be 0. So I've got 2a plus b plus c plus d is 0. And then the linear coefficient must equal the linear coefficient. So that seems fine. So we've got a plus 2b plus c is 4. And then the constant must equal the constant. So b plus c plus d is 0. Let's see if we can see that. Okay, that's okay. And don't forget from before, we've got that d is equal to minus 2. That might be good to know. So d is minus 2. Okay, cool. So we know that a plus c is equal to 0. That's really helpful. Take a look at equation 3. Since a plus c is equal to 0, that means that a plus c will vanish. That gives me that 2b is 4, and that forces b to be 2. So that seems pretty nice. Let's see here. So from equation 4, b plus d is 0. That forces c to be 0. But as soon as c is 0, that forces a to be 0. Okay, so we've got a, b, c, and d, and so we can decomp. So the integral of this du equals the integral of this du. Okay, so that term will vanish. That'll be a 2. That will vanish, and that'll be a minus 2. Okay, so we get the following. So the integral of this is equal to, and again we said that a was 0, b was 2. That seems nice. C is 0, right? C is 0, and then d is minus 2. So d is minus 2. Also seems pretty nice. Okay, so let's see here. So that's going to give us, it looks like, 2 times the arctan of u plus 2 over u plus 1. If you want to see that maybe with more clarity, you can go ahead and do maybe a w substitution. And that'll be maybe plus c. But remember, we can do some substitutions here. Okay, so recall from before. So we can back sub, so recall that x was equal to 2 arctan of u. And so also recall that u is equal to the tangent of x over 2, since we're in the realm of Weierstrass substitution. So even if we started with the cosecant substitution, that was all based on the fact that u is equal to tangent of x over 2 by Weierstrass. So this is x. This will be 2 over tangent of x over 2 plus 1 plus c. So yeah, really neat applications. Very handy in particular situations, but it is nice. So folks, if you like that, give it a like, give it a subscribe, and I'll see you next time.